Hello everyone, welcome back to our channel Jinko Academy. Today we are here again with our new case study for the ESS solutions. The project that we are going to discuss here is CNI, Commercial and Industrial Storage Solution. The project site is in Lebanon. The project is, as you can see here, is a 250 kilowatt, 645 kilowatt hour system. It's an AC couple system that we have installed on a site. The site was actually a rural area in Lebanon, and the site was actually a chicken farm. That chicken farm has no grid facility, and it was all being used. All the power to the site was being supplied with the diesel generator. And by using our ESS solution, by using our energy storage system, we have been able to achieve a remarkable reduction in the use of the diesel generator. 93% of the load after the installation of the ESS is being done by the ESS, not by the diesel generator. Before, the diesel generator was being used as 24 hours, but after our ESS solution, the ESS was only being used for 1.5 hours in the whole day. This solution was composed of our battery cabinets, which we call Sangiga. If you have seen our previous video, you may have known that our Sangiga battery cabinets is a 215 kilowatt hour liquid cooled energy storage cabinet, and we have used a 250 kilowatt PCS, and then it's connected to a PV inverter, which is 180 kilowatt, which is connected to the PV side, and then we are supplying power to the load. As you can see from this slide, see here, this is a SLD single line diagram for the site. As you can see here, we have connected 3 Sangiga of 215 kilowatt hour to the PCS of 250 kilowatt. This PCS can work on the on-grid and off-grid mode to get both. And then it's connected to the diesel generator, which are already on the site, and then it is connected to here for the PV inverters. This PV inverter is 180 kilowatt hour maximum power that can supply from this PV inverter. The solution has this is the whole solution with 3 Sangiga, 250 kilowatt PCS, 180 kilowatt PV inverter, and then the diesel generators, and then is supplying power to the load. If you have seen our previous video, you know about Sangiga, that it has battery racks. It has 5 battery racks, 5 battery packs. Sorry, it has 5 battery packs, and it also have its own battery management system, 2 levels of management system, one on the battery level and on the whole rack level. This is a communication topology of our Sangiga. This we already have discussed before also. This is each pack is connected to the BMS, which we call BMU here, then which is connected to the second layer of BMS for the whole rack. Then it's connected to this third level. On the other side, maybe on the PCS side, or a single EMS, which we call SCU, then connected to the higher level. This system, this liquid cooling system, is also have a fire suppression system. The whole cabinet have the whole fire suppression system. In case there is any fire happen, it can be extinguished inside the cabinet. This is if you can see, this diagram is about our fire system. If fire happen, then we have temperature sensors, smoke sensors. If the temperature sensors, smoke sensors, they sense there is a fire, the fire alarm will happen, start, and if it is 90, and it will send signal to the fire system, and the fire system will start working, and it will fire out. It will extinguish the whole fire. Then we are talking here. We have, as you can see here, we have discussed about our PCS that we have used. The PCS that we have used is a 250 kilowatt PCS, and the PCS has both the abilities. It can work for the on-grid mode and also for the off-grid mode. It can also have a grid following ability and also work on the grid forming ability. It depends, because since this system doesn't have this site doesn't have any grid, so we have to use a grid forming ability of the PCS sometime on the day, so that we can use the PV power to charge the batteries. If there is no grid forming ability, it won't be able to charge the batteries. On this here, we have set the diagram for our PCS, how our PCS internal structure looks like. from the this is actually not right here, for the batteries which are connected on the two terminals in the PCS, and then which is connected to the inside inverter, DC AC inverter, and then we have isolation transformer, then we have some EMC filters that which and we have two terminals on our inverter, one for the grid and other for the load, and also the PCS have so many other components that we cannot discuss here. Then we for this whole system, since we have to manage the power from the diesel generators, from the PV inverters, from the batteries, and have to supply to the load. We have to optimize the system so that we don't need to use DG most of the time. We should normally rely on the batteries or on the PV production. So that's why we need an EMS and system for the energy management system for the system. That EMS we have installed it connected to the diesel generators and the PCS and the BMS side of the battery side. This EMS provide the real-time monitoring of the control system, monitoring and the control system, the whole system for the batteries and for the also for the PV inverters and also for the PCS. It can monitor the state of charge, state of health, the power flow, and it can also have the ability to do some configuration to make the power from different sources, to optimize the power from the different sources, so that this whole system can be optimized. Okay, as you can see here, the communication of the EMS with different devices is using the LAN, using CAN, using 485, and using the dry signals. We also have a dry signals input and output, so that we can the EMS can give the signal to the diesel generator to start and to stop. And then the EMS is connected to the cloud platform, which we will discuss in the next few slides. For the operation logic of this site, we have set this site in such a way that when the SOC of the battery, the state of charge of the batteries, when it is less than 90%, since the PCS the inverter is for the battery side is 215 kilowatt, and the PV inverter is 180 kilowatt. So we have set it in such a way that when the battery SOC is less than 90%, then the PV inverter can supply the whole power that it can produce to charge the batteries and also to supply to the load. But when the when the load when the SOC of the batteries is less than 90%, more than 90%, then our PV inverter power can be limited by the EMS, and if it is more than 90%, 30% of the power can be supplied to charge the batteries, 30% of the PV of the capacity of our inverter, and the rest of the power to supply to the load. This power set point can be set according to this formula. As you can see here, P set power set point is equal to charging power plus load, and then charging power is 30% of the PCS capacity. Since the PCS is 250%, so 30% of 250 is 75 kilowatt and plus load. So the power from the PV inverter supplied is 75 for the charging of the batteries, and the rest of the power is supplied to the load. But when the SOC reaches 95%, after the 95%, the EMS will limit the power from the PV. It will limit it to 10%. So the only 10% power from the PV inverter will be used to charge the batteries, and the rest is supplied to the load, as you can see in this formula. And when the SOC reach 98%, in order for the batteries to not be overcharged, we have to limit the power from the charging power from the PV to 0. After the 98% SOC, all the power from the PV inverter directly goes to the load. It doesn't charge the battery at any time. So this is how this whole operation logic of the system work. And in this all scenario, in this all system, in this scenario, where the DG will play its part, if the battery SOC keeps going down, supply keeps supplying to the load, and PV is also supplying to the load, but somehow if the battery SOC goes less than 20%, at that point the DOI signal from the EMS is the dry contact signal will send a command to the diesel generator, and the diesel generator will start working, and then it will charge the batteries. And when the SOC reach 30%, the diesel generator will stop again, and then this will keep supplying power to the load. When the SOC go 20% below, then again start, then keep supplying to the load. So in the normal way, in most of the time, all the load is supplied by PV inverters and from the PV side and from the battery side, and diesel generator will only work when the SOC of the battery go less than 20%. This is the whole this same thing that I have said before. Here you can see the monitoring system of our EMS. EMS has also have connected to a HMI, so that we can monitor and control, set the parameters according to our requirements. In here you can see the three different scenarios, three different monitoring and control sides of our EMS HMI. On the front side, you can see this interface shows the real-time monitoring of the whole system. It can show you the battery SOC, the voltage of the SOC batteries, and it can also show you the power flow from the batteries to the load, to the PCS, from the PV inverters to the other parts of the system. It can all show you this. And on the second side picture here, we have shown you the EMS PV inverter power limit threshold. We can also, as I said before, that we can set the power limitation for the PV inverters and the batteries and the SOC. We have shown you this here, that how the SOC power and SOC and the battery PV power can be limited according to different values. And in this part, we can see the more detailed parameters of the batteries of the Sangeeta cabinet. If you click on the battery side here, you can see you can get this interface, and this interface can tell you about everything about the SOC, about the SOG of the battery, and it can also tell you it can also show you to the cell level all the information of the system. It also can show you the information about our fire control system, about the liquid cooling system. Everything can be monitored from here. This is the same monitoring system that we have said before. The EMS is connected to the cloud platform. Since EMS only can be monitored locally on the site, we have to connect it to the site. So we connect it to the EMS HMI. This is a router, and using through Modbus TCP IP protocol, and then we connect it to this system IoT router. And after connecting to this and connected to the internet for using a 4G SIM, we can monitor and control the whole system using the cloud platform of the Jinko EMS cloud. Data analysis. This is the same thing we have said before also. As you say, if the SOC is less than 90% and greater than 20%, the PV power is 100% supplied to the charging the batteries and to the load, as you can see here. When the SOC of the batteries of the battery cabinets is less than 95% and greater than 95% or 98%, between that, it supplied 25% power to charge the batteries, as you can see here. And when this SOC value goes to 98%, the power from the PV inverters is set to be 0 to charge the batteries. It all supplied to the load, so that we can avoid any kind of overcharging. The conclusion of this whole case study is that our ESS CNI solution can be used in this kind of remote sites which do not have any grid, which are using the fossil fuels by diesel generators to supply to the load, which is very costly and which is not environment friendly. We can use our CNI solutions, this kind of solutions in this kind of sites to limit the use of this kind of power generation equipments, devices like these generators, and we can totally rely on our ESS side, which can be very useful for the customer to save the cost of the fuel, and also is very environmental friendly. Thank you.